So we're going to start out college algebra this semester talking about real numbers and their properties. So you've probably seen a diagram like the one I'm about to show you here to begin with. Sometimes it's presented a little bit differently, but this is my favorite way to draw it because it embeds things. So I would just start out by drawing a big giant rectangle and splitting it into like 2/3 and 1/3 just for spacing, okay? So as we start with that, the big outer rectangle on the left is going to be the rational numbers, and I'll go back and I'll fill in some examples of them, but I wanted to get them all labeled first. And then on the right-hand side, there are our irrational numbers. And then inside of the rational numbers side, draw another rectangle. And we're going to break it down a little bit further, be a little bit more specific, and we're going to write integers. And inside of the integers rectangle, another rectangle. And we're going to write whole numbers. And inside of whole numbers, one more rectangle, and we're going to write natural. And put in parentheses next to it counting, because they're also sometimes called counting numbers. So these are our categories. And I actually want to start with the one that's on the very inside. So the natural numbers, also called the counting numbers, are the ones that you first learn when you first start counting as a child. So what number do you first learn to start counting with? 1, right? We start with 1. So our counting numbers are 1, 2, 3, and so on. So if I ask my 6-year-old to start counting, she always starts with 1. It's what's natural. But very quickly along the way, you discover that there's a need for something that even the Mayans did not have, and you need the number 0. You need it. So if we add in the number 0 to the numbers we already have, we actually call those the whole numbers. So the whole numbers are 0, 1, 2, 3, and so on. Okay? So all the natural numbers are also the whole numbers. That's why they're inside the rectangle. And then somebody, I don't know, maybe 2nd or 3rd grade, starts messing with your head. And they say something like, well, what's 2 minus 5? And you're like, well, you can't do that, right? You can't take 5 away from 2. That's just not possible. But then you learn somewhere around 5th or 6th grade that, yes, indeed, it is possible. And those are called negative numbers, right? And you start working with negative numbers. So my 5th graders are not quite there yet. So I'm not sure if it's the end of 5th grade or beginning of 6th, but they're going to get there pretty soon. So we need all the negative numbers. So for right now, here put ... and then -3, -2, -1. And then we still have all the other ones too. So the integers include all the things we've already had before, 0, 1, 2, 3, and so on. But they include what are called the additive inverses, the negatives of those same values. And 0 doesn't have an opposite value, or you could say, more accurately, that its own opposite value, right? He sort of pairs with himself. And it is in 4th grade or earlier that you start working intensely, even younger, that they actually start talking about it. But you need what are called rational numbers. So numbers that are not whole, right? They're not positives and negative whole numbers. You need things like decimals and fractions, right? Decimals and fractions are necessary, right? Like, did I eat half of the pie or did I eat a 3/4 of the pie? How much of the pie did I eat? Okay, so these are going to include, and you don't need to write them out because you can't do that, of course, but just write fractions and decimals. And understand that all the numbers that we've already discussed are also called rational numbers. So 0 is a member of the whole numbers, the integers, the rational numbers, and this whole big giant box, which is called the real numbers. That's what this whole box is. It's all the real numbers. Okay? So once you find a number or want to talk about a number, you can classify it as multiple different types of numbers. Some are very specific, right? So if I have the number 3, the most specific classification is that it's a natural number. but it's also an integer, and it's also a whole number, and it's also a rational number, and it's also a real number. It's all of those things. Okay? Irrational numbers. There are some numbers that don't fit in the categories that I've already described. They're not decimals like 0.6, and they're not fractions like 4/3 or 3/4. Can you think of any other examples that might not fit that you know of? Pi is a really good one. Pi goes over here. What's that? E. Yes, E goes over here. Some others that you might not think about are like square root of 2. So these are the numbers that would be if you tried, non-repeating and non-terminating, meaning they don't end. Decimals. So believe it or not, if somebody has told you in the past that pi is equal to 3.14, they lied to you. They did. It's not. It's a great approximation. It's a 2 decimal approximation, but it is not equal to 3.14, nor is it equal to 22 over 7. 22 over 7 is actually a better approximation, but it's still not equal to that value. Okay? Square root of 2, if you put square root of 2 in your calculator, it's going to spit out 1.414, I think, are the first 3, and then it's going to keep going, but nothing's going to have any pattern to it or any way to sort of shorten it besides just chopping it off and rounding something. Okay, so that's what irrational numbers are. Now, there are numbers outside of the real number system, and we will get to them later on in this course. Can you think of any other number that I haven't included on here so far that you might have seen? Do you have one?
Infinity?
Infinity is a concept and not a number. That's a good idea, though. Have any of you ever heard of the number I? I is the square root of -1. That's what it actually is equal to. Call it imaginary numbers. Not imaginary like your imaginary friend. No. Right? It's a terrible word. Absolutely terrible. But that is the name that people have given it. So we will get to imaginary numbers like April. So it's a long time away. For now, this is where we're going to rest for a while in our real number system. So some properties of real numbers that we have. The first one is the one that people tend to remember, right? This is called the distributive property. So it says that I can multiply across parentheses with addition or subtraction inside of the parentheses. So this is -3x plus 12, right? So you multiply -3 times x and -3 times -4, and this property is called the distributive property. The second one says that if you have multiplication, and it's one direction, that if you change it and you go the other direction, it's the same value, right? 5 times 2 is the same as 2 times 5. So y times x is the same as x times y. You have the ability to switch the order around. This is what makes multiplication facts easier for kids to learn to begin with, right? Once you get up to the 8s tables, I mean, like you've done the 7s and below, you already know half of the work. So this is actually called the commutative property. The next one actually says that when you have multiplication of 3 facts like together like this, that we can change the order of the multiplication by regrouping. We can regroup the parentheses. In other words, it's perfectly acceptable to multiply the 4 and the 5 together like that, and then attach or multiply the y afterwards. And regrouping parentheses where the order stays the same is called the associative property. The last two that we're taking a look at here have to do with absolute values. Sometimes we think about absolute values as simply ignoring negatives, right? It just becomes the positive number. And That is a true statement when we're looking specifically at numbers. A more accurate description, though, is that it's a distance. For example, if I tell you the distance between where I live and where I work, I would never tell you a negative, right? But it's different, right? Like if I'm going from work to home or from home to work, I'm going in a different direction, but it's the distance that I report. An absolute value is simply a distance back to 0. So if you're at negative 3/4, you're on the left-hand side of the number line, but you're still 3/4 away from 0. And the same is true if you're on the positive side. You're 3/4 away from 0. And what this is actually talking about is that the additive inverses, so they're additive inverses because if we were to add 3/4 and negative 3/4, what would we get? 0. And that's what makes them additive inverses. They add together to give me 0. Additive inverses have the same absolute value. All right, to continue our idea that I mentioned already about absolute values, we actually have a definition. So go ahead and write this definition that's in the black part at the top on your paper. The distance between points A and B on a number line is the absolute value of A minus B. If you actually have a number line, you often count spaces, right? I've been working with my kids on fractions and counting spaces to find distances between fractional values. So this is the distance between. Now the reality is I could write A minus B in absolute values there, or I really could write B minus A in absolute values and it will work as well. One of those numbers is positive and the other one is negative, but the numerical value will match. So the absolute value takes care of it. So we're going to take a look on number 6 at finding the distance. We're going to do it both numerically, like algebraically, like I've just shown you, and then also it describes it as being on a number line so that we can talk about why that works. So according to the definition, I want to find the distance between negative 3 and the opposite, right, subtraction of negative 14. So this is literally what that question asks me to do with that definition above. It asks me to do it with a number line, and I'll do that in just a second, but with the definition. So what do you remember about the opposite of a negative, like those two negatives right beside each other in the middle? Yeah, they change to positive, right? So it's the opposite of a negative. So this is actually saying that I have negative 3 plus 14. And what is negative 3 plus 14? It's 11. And the absolute value of 11 is 11. But notice, if I had done this in reverse and I'd started out by saying negative 4 minus negative 3, I would have ended up getting a negative 11 in the absolute values, right? But then the absolute value of negative 11 is still 11. So the order doesn't make any difference. Now, from a number line perspective, since it asked us about that as well, here's my number line. Whoops. And I need to have 0 on there. We'll put 0 on the far right because my numbers are both negative otherwise. And I need the numbers negative 3 and negative 14. So here's 1, 2, 3. So here's negative 3. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And here's negative 14. And what I'm literally counting is the space, not the hash marks, but the spaces that are available between the values. So let's try an orange color. How about yellow? It'll be a little bit brighter. So I want to start with, it doesn't matter which direction I start, but I want to count the distance. I'll just start on the left from negative 14 and count over. So this is 1. Wow, that's not the pin I struck I meant to get. Let's try again. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 11 spaces between if I count it on a number line, and I get the number 11, again, from another point of view. Okay, we're just hitting on a whole bunch of different topics. The next topic we're going to hit on is exponents. When n is a positive integer, then a to the n means that we multiply by a n times. Now, 7 and 8 are very similar questions. Of course, the difference is the parentheses, right? And the parentheses actually make a lot of difference. Because when we have number 7 and it says negative 3 to the 4th, what that really means is that I have negative 3 times negative 3 times negative 3 times negative 3. I have negative 3 4 times. So if I have 4 negatives, do I end up with a positive number or a negative number? I end up with a positive, right? Every 2 sets of negatives become positive. So if you want to work it piece by piece, a negative and a negative 3 becomes a positive 9. And this negative 3 and negative 3 becomes another positive 9. And then what's 9 times 9? 81. But the difference on number 8 is it's not negative 3 to the 4th. Yes, there's a negative, but the value that's raised to the power 4 is the 3. Okay, that's how it's distinguished differently. That's why the parentheses were used on the first one, and they're not on the second. It's because on the second one, what it really means is, yes, there's a negative, but I actually have 3 times 3 times 3 times 3. It's still 81, but it's negative 81. Because there's only one negative here instead of 4 of them. Any questions so far? This should be review stuff, but if you do have a question, please let me know so that I can clarify things. Order of operations. So order of operations has this wonderful acronym, maybe that you've heard of. Have you heard of PEMDAS? Did anybody learn, please excuse my dear Aunt Sally? It's not exactly true. A more accurate way to think about it is that the M and the D and the A and the S kind of go together. There's not an order to them. So literally, we could actually talk about this as PEDMOS, and it'd be okay. Or PEDMS. Obviously, none of it's very, pronounceable. This one is, so that's one we use. But there's nothing special about the multiplication and division or the addition and subtraction being in those orders. They're actually grouped together. So once you get to that part of the problem, you just move from left to right. So let's take a look at this example. This one is 5 minus, and we've got absolute value of 4 minus 2 times 3. So the P at the beginning, do you remember what that stands for? Parentheses. So I'm going to start with the parentheses. So inside of the parentheses, I've got the 2 times 3, right? What's 2 times 3? 6. So I'm going to rewrite everything else, not leaving any of it out, like this. Now the reality is that those absolute values are really another set of parentheses. They're like parentheses on steroids. They've got another purpose too, right? But they're still a bracketing agent. They still tell us that I have to do what's in here before I can move outside. So I still need to work inside what's there. So this is 4 minus 6. That's inside the bracket. So what is 4 minus 6? Negative 2. So now I have 5 minus the absolute value of negative 2. But I haven't finished that part yet either. What's the absolute value of negative 2? It's 2. So this is really just 5 minus 2. And 5 minus 2 is 3. Now, obviously, this one didn't have all the components of PEMDAS, right? I have one that has a couple more, so let's use that one next. A couple more, actually. So we're still going to be starting within parentheses. So inside of this set of parentheses, there's 2 things going on. There's subtraction and there's multiplication. So which one am I going to do first, the subtraction or the multiplication? The multiplication. And again, that's because the MD that's grouped together comes before the AS that's afterwards. We multiply before we add or subtract. So over here, we are in fact going to multiply first. So what is 2 times 8? 16. You got it. Now at the beginning, I have -2 minus still the 3. I mean, like all that stuff stays the same. But now I have 5 minus 16. I'm still inside my parentheses. What is 5 minus 16? That one's -11. Now, while there's still parentheses here, the parentheses don't fall under the P parentheses category. All this parentheses is doing now is not recommending, but telling us we need to multiply, right? We need to multiply that -11 by what's next to it. In particular, it's a -3. So at this point, all I have left is some sort of addition or subtraction going on right here, eventually. And I've got the multiplication going on right here. So I'm going to write my -2 down, and I'm going to rather ignore it for the moment. What is -3 times -11? Positive 33. And that does mean plus 33 at that point. And then -2 plus 33 would be 31. So the only thing about order of operations that I want to mention is that the reason we do it the way we do it is because everybody does it this way. That way, when you do a problem and I do a problem and you do a problem, we all get the same answer. So we need some kind of structure. So this is definitely like a human-imposed structure upon the mathematics, just so that we're all doing the same thing. There's nothing inherently like right or wrong about it. It's just what we've decided as a mathematical community somewhere back in the day to make sure that we all have the same thing. All right, we're going to pause there. I have just a few more examples. Let me give you the suggestion then that inside of my math lab, I need to adjust the dates. You're welcome to start working on this assignment. We will finish this next time. We will also finish P.2 next time. So if you choose not to work on this today, you'll have 2 assignments to do between Wednesday and Friday, okay? So I would encourage you to get started on this. There's a few things we haven't covered, and when you get to those things, just either do them if you know how to, or pause and don't, and come back to it on Wednesday, okay? Have a great rest of your day.